So someone asked for some sort of background references. So there's a few there. The original sort of article where, in a sense, we rediscovered Thomas's connection and so on is this article with Toby Bailey and Mike Eastwood. It's in Rocky Mountain. And that's a very good article for just the basic calculus and everything. A lot of what I've been talking about so far, as is probably the point of view I've been taking is a lot that I put forward in this article from 2010, where I'm introducing this role of the scale tractor a lot, I suppose. And in terms of tractor calculus in general, because it applies much more generally than just the conformal geometry, so it applies to any parabolic geometry. These are kind of curved versions of the homogeneous spaces where you have a semi-simple Lie group, quotient, a parabolic subgroup. So if you think of that homogeneous space, there's a curved version called a parabolic geometry. So, and tractor calculus applies to all of those simultaneously, and there's actually an awful lot that you can prove uniformly for the whole class of geometries. So, and the sort of initial steps in the sand, as it were, in that direction are in there. Related to that was a sort of conference article I also wrote with Andy, which specializes some of the general machinery to what we call irreducible parabolic geometries, of which, for instance, conformal and projective geometries are examples. And then, related to today's talk, there's this article about holonomy reductions of Cartan geometries, which is a very general point of view of what you get out of holonomy reductions. So I'll try to make that clear if I get started quickly. All right. Okay, so, and related to this, this is related to the point of view that I mentioned before, right at the start, that you can think of a Riemannian geometry as what? Well, you can think of it as a conformal geometry plus something, right? So you could put the scale back in. But that's kind of, I mean, it is what you want to do, but if you just do that, you're doing nothing, right? So you're just saying a trivial thing that you can forget the scale and you can put it back in. So, so in a sense, the right thing to do, I claim, is to put, if you want to think of Riemannian geometry from a conformal point of view, you put the scale tractor back in. and I'll try to explain in one context today, in connection with conformal compactification. But actually, this idea even applies if you're not doing conformal compactification, but let's restrict ourselves a little bit. Okay, so let's remind ourselves about conformal compactification. Well, what conformally compact means, or what it will mean for this lecture at least. So now I'm going to change the dimension of the manifold, the bulk, as it were, to D rather than N, because it's traditional in this, when you talk about conformally compact things, to take the boundary to have dimension N. So to end up with formulae that look the same as other formulae you see, it's a good idea to do this. So think of D as being N plus 1 now. So this is going to be a manifold with boundary. And I'll call the boundary sigma, because I like to think of it as a kind of hypersurface. So I'll draw this picture here, but the picture doesn't necessarily make much sense in the context here, but let me think of the picture like that. So here's the boundary. The interior I'm going to call M plus. The whole thing, the manifold with boundaries, M. So, but the picture might look different, you know, so it might be that it looks like this, and the boundaries here and is not connected, you know, so there's two bits of boundary, or whatever. I don't care, because actually a lot of what we're going to be doing is sort of, well, everything is sort of local around the boundary anyway. Okay, so M plus will be the interior, and we will, so suppose, so what we'll do is we'll say that M plus G plus is conformally compact. And this can be some signature PQ as usual. Two things. So first of all, there exists a defining function, call it R, for the boundary. So what this means is that the boundary is the zero locus of the function, and so dr is not equal to 0 for all points along the boundary. So that's what I mean by a defining function. And next, there exists some metric G on M such that the physical metric, if you like, G plus, or the geometric metric, depending on your background, is R to the minus 2G on the interior. Okay, so that's how I want to think about it. So you think of this as having this physical or geometric metric to start with, and then we're going to say it's conformally compact if you can find some defining function for the boundary and then some metric that's compatible with G plus in this sense. And of course, what you see, if you'd never seen this before, and I'm sure you all have, is that this is a metric that goes to the boundary. R to the minus 2, of course, is going to blow up at the boundary, and so this G plus doesn't extend to the boundary in a very specific way. Okay. Now, so the defining function R and the metric G are not sort of fixed. They just have to satisfy those relations. So, but each defining function R determines a metric G, or is basically equivalent. Of course, there's a choice of sign here. So typically, you ask R to be positive. And then these match, of course. So, and now G determines a metric that I'll call G bar on sigma. Okay, so just by restriction, it's the first fundamental form, if you like. So you along sigma, you restrict G to tangent vectors, and you get G bar. But we can change our mind about the defining function because it's not part of the data. So you can get a new defining function by multiplying by a positive function. So we should look at what happens when we do that. Let's say it's e to the f times the old defining function. Then this determines a metric. And the metric you get is e to the 2f G bar. And so what you get on the canonically, you just get a conformal structure on sigma. So we'll write that like sigma, so bold C, but overline to be the conformal structure that we get on the boundary canonically from the situation. Okay, so in general relativity, this idea, which I believe was introduced by Penrose, was used to study isolated systems. So it was a way of sort of mathematically making a reasonable structure in which you could study isolated systems and radiation and so on. This last point has also attracted interest in general mathematical physics and related differential geometry, I would say. So there's quite a big program to understand the link between the conformal geometry that you get here and the pseudo-Riemannian geometry that you have on the inside. And in the ADF C/T correspondence, this is the idea, but now to study with string theory. So they look at conformal field theory on the boundary and the related string theory on the interior. And of course, This is even related to representation theory when you look at the model. So there are problems you can set up in representation theory. You're looking at the same thing. So this fits into part of a very general program. Yeah, so let me just talk about it rather generally at the moment rather than specifically for GR. Okay, so first of all, what's this mean for us, or what's the right way to view this within our conformal picture? So the first sort of trivial step is that I want to think of the bulk manifold. So in the math physics literature, they often call this bit the bulk, so, or the entire manifold I'll call the bulk. But I want to think of that as having a conformal structure, of course, and study it that way. So remember, if a metric on a conformal structure is given by taking the conformal metric and multiplying by some scale to the -2. So here, so if tau is a section of this, for instance, so densities of weight 1 positive ones, then this gives me a metric G on the whole of M, including a metric that goes to the boundary. So what's this G plus? Well, if I take R times tau, then that gives me a section of densities of weight 1, but it's not positive anymore because it's 0 at the boundary. This is what I'll call a defining density for the boundary. Okay, so let's call that sigma. So this defining function times tau. And then G plus is now sigma to the -2 times the conformal metric. So that's the first step to putting it in our kind of language. Okay, so what I want to see actually, first of all, is that this situation of having conformally compact metrics arises just automatically in a certain sense in the conformal picture. So let me start that. So this is part of a sort of general idea that I usually call geometry of scale. But scale being slightly more general than the usual notion of scale. So remember from lecture 3 that we say that a conformal manifold equipped with one of these scale tractors is almost Einstein. So it is almost Einstein if this thing is parallel. So this is a section of the standard tractor bundle. So it's parallel for the standard tractor connection. So remember, that means that the scale sigma satisfies that equation, that Hessian type conformally invariant equation. So then necessarily this parallel tractor takes the form of being 1 on D now, sorry. This Thomas D operator acting on sigma, where sigma is the scale. And also where, so when you have this where sigma is non-vanishing, on the region where it's non-vanishing, the metric that you get from sigma is Einstein. Okay, so you take a conformal manifold, you insist that it's equipped with one of these parallel standard tractors, and then the parallel tractor is of the form D of sigma. When you form the metric from sigma, or the thing that should be the metric, it'll blow up where sigma is 0, but where it's not 0, then the thing has to be Einstein. And whether it's has cosmological constant positive, negative, or 0 depends on the length of I. So remember, I squared is roughly minus the scalar curvature. constant because I is parallel, of course. Okay, so here's the question, or some questions. What's the zero locus of sigma look like? Okay, so is this a good idea? Is the zero locus some sort of horrible mess, or is it a nice set? And then the next question is, can we drop that I is parallel? Doesn't make sense in the context I'm talking about, but what I mean is, can we somehow draw something from this almost Einstein situation that applies much more generally? Yeah, of course you can. That's why I want to talk about it. Okay. So, okay, so we want to look at the zero locus of sigma and Cartan holonomy. So the point is here is there's a very general way to answer one. In one sense, if you really just want to study one, what is the zero locus when this thing's almost Einstein? It's crazy not to do it this more general way because you see a lot more. So let me say a little bit about that. But secondly, to deal with two, I want to look at things from a more elementary point of view. Okay, so to deal with this first, let's go right back to the model. So remember, we start off with R D plus 2. We equip it with a Lorentzian metric, which we called H. This gives us some groups. So going to be, let's pick that bit, the oriented bit, D plus 1, 1. That's going to act because we've now got this. So, and we get a null cone on which things act. So this is the cone of null vectors in RD plus 2. And of course, so the group acts preserving this and so on. And so this, remember, gave us a sphere with a conformal structure. And that was our model of a conformal geometry. So now what I want to do is add a symmetry breaking to that. So I want to think of Riemannian geometry, or this conformally compact situation, as arising from a symmetry reduction of this. So what I want to do is add to this now so this is the Riemannian model. So, but I want to add to this a space-like constant vector. So you think of this as just being zeros and 1 at the end. Okay. So then I squared, according to this metric, is going to be 1, at length 1. And then this constant, this vector can be thought of as a constant vector in the affine structure up here. And it's going to give us a polynomial, a distinguished polynomial, where you just contract it into the coordinates in the standard way. Let me call that sigma tilde. And I can look at the zero locus of that, for instance. So this equals 0 is some sort of hyperplane. And I can look at the zero locus. And it's easy to see that that's a subcone. So it's sort of eye sticking out there. So this is a subcone. I'm focusing on the forward cone. And I can look at where this is 1, for instance. Why not? So that's another hyperplane. And that intersects this null cone. Okay, so what does that give us downstairs? So downstairs, this subcone, well, we can forget the other dimensions. It must give us a conformal structure on a sphere of one lower dimension, right? So here it is. It's a sort of hemisphere in our original sphere. And it's going to have a conformal structure because for all the reasons that the cone gives us a conformal structure, the subcone does. On the other hand, this section here really is a section of the, remember this was a ray projectivization. So this really is a section of the ray projectivization, meaning that every null generator on this side will intersect that in one point. And so down here, this will give us a metric, I'll call it G plus, which is actually a hyperbolic metric. Why is it hyperbolic? Well, you can check that the induced metric is hyperbolic. This is just pulling back, remember this is pulling back the metric up here. But of course, the real citation for that being hyperbolic is probably 500 BC, right? This is a conic section. So this distinguished, this vector here in Rd plus 2, which gives us this distinguished linear polynomial, gives us a hyperbolic metric here and a conformal infinity. In fact, we could go to the other side and put the minus 1 section and we'd get a doubling, right? So we'd get hyperbolic structure on the other side. So it's just, you just look, look at the way I've picked this. So when you put this equal to 0, you're just losing the last coordinate. So you take your formula for the, yeah. So this is, okay. Now, by the way, I meant to say, so what about in terms of groups? Well, the subgroup preserving, so what's the isotropy group of this thing? So G got reduced to H, which is the isotropy group of that fixes the size. So this is going to be a copy of SO D1. It'll knock off one of the, because it's space-like, it'll knock off one of those parts of the group, if you like. So, and now what's happening here is this is the orbit decomposition of the sphere under H. Okay, so it has two open orbits and a closed orbit. So this is an orbit decomposition. So, so it's an orbit decomposition of G mod P, right? So this sphere we can think of as being G mod the isotropy group of a point. So this is the isotropy group of one of these null generators, so it's a parabolic subgroup, or the stabilizer of it. So this is a parabolic subgroup. So this is a homogeneous space, and now here we have this orbit decomposition. So this is the orbit decomposition via the action of H of this group, of this homogeneous space. Okay, so we want a curved version of that picture, all right, with the reduction now. Okay, so what's the curved version? Well, I already told you a curved version without the yellow bits was something to do with tractors. Let me say it in a slightly different way. So we have, in the model here, we have this. We have a parabolic subgroup, a semi-simple Lie group, and we have our G mod P, which is our homogeneous space. The curved version of this, said another way, is what's called a Cartan geometry, so we'll call it curly G. That has also fiber P, right, the same group as fiber, but this is not a group. It is a principal bundle, and it's a principal bundle over our manifold. This has the Moore-Cartan form, right? So just the thing that takes left invariant vector fields to the origin. Yep. Sorry? No, P plus is just a ray projectivization. P is the subgroup in G that stabilizes a null ray. Okay? I can draw a picture of the group if you like, but it's more important the idea. So it's the isotropy group. So G acts on the sphere and it's the isotropy group of a point. So it's a parabolic subgroup. Okay, so the group G is equipped with the Moore-Cartan form. That's just a standard thing from Lie theory. A Cartan geometry is equipped instead with a Cartan connection. So like the Moore-Cartan form, this gives us a mapping from the tangent space at each point of the principal bundle to the Lie group. Sorry, the Lie group of G. But this is not a group, and this is a vector space, a vector space map. However, this does have other equivariance properties, so it picks up the vertical vector fields and maps into the Lie algebra of P, and so on. So it has some equivariance. I won't go into all that. Now this is equivalent to the tractor connection, basically. So it's just it's a principal bundle picture, or in this case a Cartan bundle picture of the tractor connection. Except it's the Cartan connection, and was discovered by Cartan earlier. Okay, so by the way, if you want to think of it that way, if you start with the tractor bundle, this is the adapted frame bundle for the tractor bundle, and you can recover the Cartan connection from the tractor connection, and it's quite easy actually. Okay, so now there's this theorem I'm writing using a big font today, using up my board too quickly. So this is in that article I mentioned around here somewhere on the other board. So there's this curved orbit decomposition theorem. Okay, so let me write this carefully. So suppose, or not so carefully, but reasonably carefully. So suppose you have a Cartan geometry. Modeled on G mod P. Okay, so in this sense, so one of these, there's a very general notion. I haven't told you all the details, but so, and this is endowed with a parallel tractor. That gives a holonomy reduction Okay, so what am I saying here? So we have one of these Cartan connections, Cartan bundles and connections. From that you get tractor bundles. So you take any representation of the big group G, then a Cartan connection gives you a linear connection. So you get some kind of tractor bundle by forming associated bundles. Important thing, so if you just have a P representation, you get associated bundles. But if you start instead with a G representation and restrict it to the parabolic subgroup, then you get not only an associated bundle, but one with a connection from the Cartan connection. So these are the tractor bundles. So from any representation of G, we've only so far looked at the standard representation when we were doing the standard tractor bundle. Okay, so the Cartan connection gives us a linear connection on there. So I'm saying, suppose we have a Cartan geometry and it has a parallel section of one of these bundles. Then that will determine a holonomy group, which is roughly speaking the group that preserves that parallel object. Okay, the isotropy group of that thing. May be trivial, but it's not. It's often not. Then, if you have that, then the manifold is canonically stratified. it's stratified into a union of strata, so that are parameterized by the double cosets. And this is in a way that's locally diffeomorphic to the the H orbit decomposition of the model. Okay, so you look at your homogeneous space, G mod P, look at how what happens under the action of H, then this decomposes into strata, just the orbit decomposition. What this is saying is that when you do this with a curved Cartan connection, you ask for a parallel object which corresponds to reducing to this group H in the model, then you get a similar stratification of the curved structure, the underlying manifold. And locally it looks just like the model. And the second thing is that on each of the components of the strata, there exists a Cartan geometry on the MI of the same type as on the model. Okay, so the general picture is you have your model, and then you have some kind of some sort of reduction to a group H, and you get some sort of strata decomposition of the model. So this is G mod P under the action of H. When you do a curved case, if it has a Cartan geometry modeled on G mod P, and then you ask for a holonomy reduction where the holonomy group is that same group, and I haven't said to you completely how to make sense of that, but there is a way, then you get a corresponding decomposition in the curved case. And locally, about any point, it has to look like that in the model. In other words, the sort of singularities and so on in the way these orbits come together have to be no worse than they are on the model. So if you get an embedded hypersurface in the model, you get an embedded hypersurface in the curved case. Okay? Of course, there's always the possibility in the curved case that there's no, you may be dealing with just part of the thing. There may be no singularities, but they can't be any worse. Okay. So that's the general result. So when we apply it to our current situation, we can just read off what happens to this question one. What was the zero locus? When we look at the specific holonomy reduction that's modeled on this thing here, we get this result. So now we're back to conformal geometry. So, by the way, I was saying parabolic here. This doesn't even need parabolic. You just need a Cartan connection. It doesn't matter whether P is parabolic or not. It's just a result for Cartan geometries. So if you have a conformal manifold with this parallel standard tractor, then in particular you get this holonomy reduction I was talking about in the curved case. So it's going to have this parallel standard tractor. So this almost Einstein structure is going to be stratified according to the strict sign of sigma, which is what you get when you take your parallel tractor and contract it into the canonical tractor I. Okay, so the top slot of the parallel tractor. Okay, so the sort of picture that you might get, I'll go through the cases, but you have sigma positive, sigma negative, and sigma 0. A closed orbit, or a closed curved orbit. Okay, so, but I haven't finished this theorem, so if I squared is not equal to 0, so in other words, G plus, so G plus being sigma to the minus 2 of the conformal metric, so where this is defined, it will be Einstein and non-Ricci flat. So if that happens, then either the 0 locus of sigma is empty, whoops, which is always possible, of course, or, the more interesting thing, it's forced to be a smooth hypersurface. A smooth embedded hypersurface. Okay? It has to be a smooth embedded hypersurface because that's what happens on the model. And the theorem says it can't be worse. If I squared is 0, so this is the case that G plus is Ricci flat where it's defined. Okay. Then either the 0 locus is empty again, whoops, or or the 0 locus take away some isolated points is a smooth hypersurface. Okay, so there are isolated points where things can go wrong because that's what happens in the model. But away from those, when you remove those isolated points, then you get a smooth hypersurface. Okay, well, just look at this first case. So what this is saying is when you're in this case where I squared is not equal to 0, so where the metrics define it's Einstein and not Ricci flat, it really does look something like this picture. And what you get is a gluing so this first case looks like that, and so you get a gluing, how do you spell gluing? Probably not like that, but anyway, so it's a gluing along the conformal infinity of Poincare Einsteins, let's say. By Poincare Einstein, I don't necessarily mean negative curvature, but basically, this is a gluing along the conformal infinity of conformally compact metrics, which are Einstein in the bulk. Okay, so that's what you can see already just from this general holonomy reduction theory. Now I want to show you that in fact you can see a lot of this using much more elementary tools, and although, as I say, this result is powerful because for the case where you really have a holonomy reduction, it just works completely universally. On the other hand, these elementary tools tell us how we can go answer question 2. Can we drop that the thing is parallel? Okay, so maybe I'll go to the other board for change. Okay, so using no technology at all. Okay, so now we'll consider a conformal manifold equipped with a scale tractor, but we won't ask that it's parallel. So where I equals just 1 over d dA sigma. So this is a density of so sigma is just some density in here. Of course, we don't want it to be identically 0. In fact, here's a definition. If I is nowhere vanishing, which is what we'd always want, then we'll say that MCI is almost pseudo-Riemannian. Okay, because if the scale tractor is nowhere 0, it's just part of the jet of sigma. So if I is nowhere 0, then sigma cannot vanish in an open set. So you'll get a metric almost everywhere if you have this condition that I doesn't vanish at any point. Okay. Okay, so let's see that we get a result like we had before using completely elementary ideas. So if I want to take this conformal manifold equipped with the scale tractor, if this has the property that the scale tractor is bounded away from 0, so this is epsilon some small number, say, the length of the scale tractor, of course, may be positive or negative, but we just want we want it to be away from 0. Then the 0 locus of sigma is either the 0 locus of sigma is equal to the empty set, which is always possible, as I say, or it's a hypersurface. It's smooth, but I'll drop that word. So it's an embedded separating hypersurface. And what's more, the sign of the normal squared, so whether it's sort of space-like or time-like hypersurface type thing, is just equal to the sign, of I squared. And finally, if the conformal structure has Riemannian signature and I squared has negative length, in other words, the scalar curvature is positive, then the 0 locus of sigma is equal to the empty set. There is no 0 locus. Okay, so this is not using holonomic reductions or anything because we don't have any parallel tractor. We just have something that's very close to a pseudo-Riemannian manifold, except it's slightly generalized and the scale may be 0 in some places. And we're asking that the scale tractor has length bounded away from 0. Okay, so the proof just uses the way this thing looks, the scale tractor. So remember we expanded this out. So perhaps I won't do it again for reasons of time, but you just multiply the two scale tractors together using the metric, and what you get is that you get G, the conformal metric, contracted into grad A sigma, grad B sigma, minus 2 over D sigma Laplacian plus the trace of Schouten acting on sigma. So that's all you get from the length. So everything really applies from looking at that. And recall that where sigma is not 0, then we can work in the scale of sigma, and we get I squared is minus the scalar curvature of G naught over d minus 1, where G naught is equal to sigma to the minus 2 of the conformal metric. Okay, that's because these terms drop out, and it's just that term surviving. So basically, this is the scalar curvature, except slightly generalized, because it applies where sigma is 0. Okay, but along the 0 locus, let's look at what happens to this thing along the 0 locus. What we have is that I squared is just equal to GAB grad A sigma grad B sigma. And we asked that that be greater than epsilon. That was what we were assuming, that I squared was bounded away from 0. Therefore, the gradient of sigma, grad of sigma, is nowhere 0 along Z sigma. Therefore, if it's not empty, if the set is not empty, then Z sigma is an embedded hypersurface, a smooth embedded hypersurface, just by the inverse function theorem. So, and also, since grad of sigma at P is not equal to 0 for P's in there, that means that sigma changes sign as you cross the 0 locus. As you cross the hypersurface, if it's not empty. Okay? Therefore, the hypersurface is separating. Next, you have that I squared, this is still along sigma, is equal to GAB. Well, it's grad A sigma, grad B sigma, but you can take that as a conormal. So NA is grad A sigma. It's a type of conormal. Therefore, the fact that the normal squared has the same sign as I squared is just obvious. And then finally, we just put it down here. If G is Riemannian, the conformal metric is Riemannian signature, then GAB NA NB is obviously positive everywhere. So if I squared was asked to be negative, in other words, if the scalar curvature is positive, where it's defined, then there can be no 0 locus. So, whoops, because I squared equals that along the 0 locus. One is positive and one is negative. Any questions? Okay, well, in the last bit of this, I want to point out a sort of converse to this, which may look more useful from your point of view. So, converse. Okay. So what I want to talk about are sort of constraints on the possible geometric compactification. So what sort of compactifications are possible? So what I mean is this. So let's start with Euclidean geometry. Okay, so here it is. There's Euclidean D space, waiting for additions. So suppose you want to conformally compactify that. Well, probably you learned it at primary school or early high school or something that you can do stereographic projection. Okay, so you set a sphere on there. If you did it at primary school, it was probably a low-dimensional sphere. And you start from the North Pole, you take a straight line through, and you identify the point on the sphere with the corresponding point on the on Euclidean space. Well, this is conformal, this map. So if you pull this back up, it's conformally related to the sphere metric. So the sphere metric conformally compactifies Euclidean space. But you get a 1 point. So the topological closure of Euclidean space under this geometric compactification, which is just going to be the sphere, is a 1 point compactification. In other words, the boundary of this thing is just a point. Well, from many points of view in analysis, that's or representation theory or whatever you want to use it for, that's can be a bit annoying. It has a lot of applications, but you're packing potentially a lot of information into a point. What happens, so this is flat, right? So this curvature is flat. What happens if we take a negatively curved thing? So you look at hyperbolic ball. So the Poincare representation of hyperbolic space, then the usual compactification is into a closed ball. So in this case, the topological closure is a ball. And the boundary of that is a sphere. No. N, d minus 1. Okay, so there's a big difference. Here we compactified and got a point. Here we compactified and got a sphere. So, well, partly you get an answer for this problem from this orbit decomposition thing. So that predicts what happens. But let's see. So what I want to claim really is it's the scalar curvature controlling this. Okay, so in fact I can only partly make that precise, but let me make the part that I can make precise. Okay, so theorem. So let M plus G plus be a geodesically complete, I won't usually put the word geodesically, but it's a complete pseudo-Riemannian manifold. And I want to put this into a bigger manifold. So I want to embed it into, actually I can change my notation here, so I'll try that, but it could go wrong. Okay, so I want to embed this into a manifold M, which will be, let's assume that this is closed, for instance. And open embedding okay, so what I mean is that both of these have dimension D, where MD is closed and has a conformal structure, and such that there exists So here's the restriction I want to make. There exists a sigma, which is a density of weight 1 on M, and on M plus, which is, I'm going to just identify with its image under this thing, contained in there, we're going to have that G plus is sigma to the minus 2 of the conformal metric that's on the big manifold. Okay, so the picture would be something like so here's my M, and here's my M plus. And I don't know about the boundary points yet, but there's some sort of open embedding in there. That's what I'm going to assume. And this thing has a conformal structure. And then the metric here is compatible in that sort of usual way, but I'm not assuming anything yet about sigma apart from the fact that it's smooth. Okay. Now let's write boundary M now for the topological boundary of M plus. Perhaps I should call it that. I'm in the process of changing notation compared to my notes, which is always dangerous. Okay. Then, okay, so here's the main point. If the scalar curvature of this G plus is bounded away from 0 on M plus, then either M equals N, we can't eliminate that, or the set of boundary points is a smooth, is a smooth embedded hypersurface in M. Sorry, did I change it somewhere else? Sorry. Yeah. Yeah, I had an M going into, yeah, anyway, you can see what I had. Right, okay. Set the scale tractor up as usual. So this is 1 on D, dA sigma. Okay? So that thing is smooth on all of M. And so is its square, its length. And what's more, this is bounded away from 0 as well on M plus. So okay, I've changed to epsilon because this is related to the scalar curvature, but it's not exactly the same. But it's still bounded away from 0. So that's what we're going to use. So this means that I squared is also bounded away from 0 on this plus its topological closure. So now let's look at what happens at the boundary points. If you take P, a boundary point of M plus, then I claim that sigma has to vanish there. Okay, so why is that? Well, otherwise, if it doesn't, then this is smooth, so it doesn't vanish in the neighborhood of P. Oops. Whoops. Open neighborhood of P. And therefore, G plus, which remember is sigma to the minus 2G, will extend into this neighborhood. But that's a contradiction because that means that G plus as it was originally on M plus, could not have been geodesically complete. Because once the metric extends, the Levi-Civita extends, and that point won't be at infinity anymore. So what we have now is that these boundary points are contained in the zero locus of sigma. Whoops. And what's more, for all P in there, we have that the derivative of sigma at P is not equal to 0 because as we explained, this GAB, grad A sigma, grad B sigma, is going to be equal to I squared, which is not 0 because this thing was bounded away from 0 on the topological closure. And so this sigma is 0 at all these points in here, but the derivative is not 0 at those points, so again it's an embedded hypersurface. And that's the sketch of the argument. Okay, so I'll stop there. I actually want to change the topic slightly, but of course it's linked. So I want to talk about conformal hypersurfaces generally. So the reason being, well, let's say obvious at this stage. So, well, let me say what I mean. So sigma, I'll take to, that'll be my notation usually. That'll be a hypersurface. So what I mean is a smoothly embedded codimension 1 submanifold. But I want to include the case, of course, that it's the boundary. Okay, so it may be also the boundary of a manifold. And that's the reason, of course, we want to look at hypersurfaces mainly today, is that we've seen that hypersurfaces turn up as the conformal infinity in a conformal compactification. And we've seen also that conformal compactifications arise automatically if you start looking at parallel standard tractors, for instance. And we've even seen that they arise automatically if you drop the scale tractors parallel and just ask some things like that its length is bounded away from 0. Okay, so what I want to do in the next lecture is use this technology to study the relationship between the conformal structure on the conformal infinity to the geometry on the interior, on the bulk. And in particular, for instance, to the conformal geometry on the bulk. And part of what's involved with that is understanding how to deal with hypersurfaces in general. So if you have a conformal manifold and you have a hypersurface in a conformal manifold, what gives? You know, so what do you get? Okay, now this is why I want to treat it separately. Is that also it's of independent interest even in GR, because this can apply, for instance, to Cauchy hypersurfaces or whatever. So there's many situations where you might want to look at hypersurfaces. All right. So one thing is that just some trivial comment. So this is going to be in a conformal manifold. So it'll have dimension D. Rather than think of a normal vector or covector in this case, it's better to give it a conformal weight. So and I want to assume that the normal to this is not null. So so such that the normal or the conormal is not null. So you know, we can normalize it so that GAB NB equals plus or minus 1, right? So allowing for whether it's space-like or time-like and so on. Now this is the conformal metric. So so this cannot be just a covector. It has to have a weight. So this is in the cotangent bundle, but has weight 1. So this thing along sigma, right? So you take a conormal that has weight 1, and that way you compare it with this thing which has weight minus 2, and get a number, namely plus or minus 1. So this is the sort of first step in dealing with submanifolds conformally. You have to have these weighted normals. Now, as you probably know, in pseudo-Riemannian geometry, the fundamental sort of invariant of a hypersurface is the second fundamental form. Wow. So if you're in that situation, so the way you get that is you just look at the derivative of the normal along the hypersurface, the conormal, and this gives you some actually symmetric. It's not hard to see this has to be symmetric. So this is a symmetric 2 tensor, and you restrict it to the tangent space to the hypersurface. So that's really what the second fundamental form is. Okay, so if you want to give a sort of formula for that in the pseudo-Riemannian setting, or indeed here we can do the same thing using the conformal metric, you can decompose the tangent space to the manifold along sigma into the tangent space to sigma. You can orthogonally decompose that into this plus a normal bundle, or don't know how we want to. So this is an orthogonal decomposition. And we can do the same here because we use the conformal metric to make the projections and so on. And so if we do that, then we can actually make a sort of formula for this by just projecting that orthogonally to be something that takes values in the symmetric square of the cotangent space to the hypersurface. And then what you get is that LAB, and we'll just take this basically as a definition, is grad A MB minus plus, depending on the sign of N, NA NC grad C NB. Okay, so this along sigma. Okay, so that's just a sort of formula for the second fundamental form. Okay, and this is independent of how n is so it satisfies this along sigma. We imagine that n is smoothly extended off sigma, and this is independent of how it's extended off. It's easy to see. Now, what's the conformal properties of this second fundamental form? So let's talk about that first. This is just a sort of classical question. So the point being that if that's the fundamental invariant for hypersurfaces in pseudo-Riemannian geometry, then what's the corresponding thing in conformal geometry? So we want to look at the conformal properties of the second fundamental form. So let's change the ambient metric by, instead of putting, we'll still call it g hat, but instead of putting omega squared, I'll just put e to the 2f there, or 2 omega. Okay, so there's still a positive function times g. And now the epsilon will be d of omega. And so now we just compute how the metric changes. So this thing is just fixed. It has this conformal weight. So remember, it has weight 1, because we're now in the conformal setting. And we look at this thing. And what we have is this is grad A NB. And I don't know if you remember the formula, but it had a minus epsilon A NB minus epsilon B NA plus GAB epsilon dot n. But also this has weight 1, so you end up with plus 1 more of these to do with the fact that it's got conformal weight 1. Okay, so there's some cancellation. And now what you do is you project this, so you hit it with the, I'll call it pi sort of AB or whatever it is, and this is going to be the Kronecker delta minus this normal with its index lifted using the conformal metric and lowered. So that gives a projector, and you do it on both indices. And then what you see is that LG hat AB, because that gives the hatted version of this, and on this side we get LAB with whatever's left. But this projection kills this thing, because this projects out the normal components, so that term goes, and you're just left with the projection hitting that, so you get plus plus the first fundamental form. You just get the induced metric on the submanifold. Okay, so we picked, of course, we picked a metric to do this. So this is the, so this is what you get for the change of this. And so what you immediately see is this classical result that the trace-free part which I'll call L0 AB so this is where H is the averaged trace part. So the mean curvature is conformally invariant. The conformal transformation of this is by pure trace. And so when you take the trace-free part, it's conformally invariant. And what we also get is that the mean curvature transforms just by taking the trace of this, and looking what happens, you get that this is that plus NA into epsilon A. Okay, so we got a conformal invariant, and that the mean curvature is not conformally invariant, but there's a nice corollary of this, that if we form this thing, this is going to be a tractor defined to be equal to 0, so defined in the metric G to be 0 NA and then minus HG. This turns out to be conformally invariant. So this is a section of the standard tractor bundle along sigma. And I'm going to call this the normal tractor. So this, the corollary is that this is conformally invariant. And H in its length is going to be equal to plus or minus 1. Okay? And the proof is just that under a change of, so we wrote this in a metric G. So when we go to G hat, so this is sort of n in the metric G, we make the G hat in this way, then what we get is 0 in a, well, hg hat, but this is minus hg minus epsilon, or epsilon dot n. But you see, if you recall that triple star from the other day, this is transforming in the way that tractors are supposed to transform. Okay, so that shows the hallmark of being an invariant object. So that's the normal tractor. Okay, well this has got perhaps the potential to play the same role in conformal geometry as just the normal vector does for Riemannian geometry or pseudo-Riemannian geometry. And indeed that's the case. So that's partly what we want to see. Okay, here's the definition. Again, a sort of classical term. So a point P in a submanifold, in a hypersurface, is called an umbilic point. Have I got the right number of L's? Perhaps it's 1. It's one of these I always misspell. If L naught at P is 0. So if this conformal part of the second fundamental form, this trace-free part, vanishes at the point, it's called an umbilic point. And a hypersurface is said to be totally umbilic if this trace-free part of the second fundamental form vanishes at every point. Okay, so that's just some terminology. Let's see how this totally umbilic condition shows up in conformal geometry. So I want to form this thing, LAB. So this is a one-form index and a tractor index. It's going to be defined to be just the tractor derivative of the normal, but in the direction of the submanifold. So this is the pullback, if you like, of the tractor connection. In other words, it's just the tractor connection differentiating in tangential directions. You could use a different index, but I want to think of the tangent bundle as being a sub-bundle of the tangent bundle of the submanifold as being a sub-bundle of the ambient tangent bundle, and the same with the cotangent bundle, because it turns out that the notation's better that way. Okay, so what is this? You differentiate the normal tractor along your hypersurface. What do you get? Well, if you compute it, you get the trace-free part of the second, you get 0 trace-free part of the second fundamental form, and then you can show that in the bottom slot, you get a divergence of the trace-free part of the second fundamental form. So the proof, which I won't do completely, but the first bit is just trivial. So let's just take the derivative in any direction of this thing. So you imagine it's extended off somehow. So, where's our normal tractor? It's way down the other end. But so you've got 0, in the normal tractor you've got 0 n and minus h. So we're differentiating that using the formula for the tractor connection. Well, if you remember how you do that, you differentiate the thing in the top slot, that's 0, and you subtract that, the thing that was in this slot. So you get minus nc there. and then you differentiate this thing using the Levi-Civita connection, so CMB. Then you add the Skelton tensor times the thing in the top slot, which is 0, so that doesn't do anything. And then it's the conformal metric times the thing in the bottom slot. So you add that, and it's got the minus sign there, so you get minus GCB, oops, H. And then minus GCH. So you imagine everything is somehow extended off smoothly, so you make sense of that. And then you get the Skelton CB contracted into B. So that's the formula for the differentiate the thing in the bottom slot, and then Skelton hooked into that contributes to it. Okay, so altogether we get that. But now this is just differentiating in every direction. So now you want to project this. So apply pi BC, which is delta BC minus NC MB to that. Okay, so this is going to project and kill normals. So it's going to kill that. We'll get 0 in that slot. And then when we apply it to this slot, it's easy to see you actually only have to apply this one projection to that. And so you get that this is just the trace-free part of the second fundamental form there. And then you use, to get this back, you have to use the cadency to turn that after projection into this formula here. Okay, but mostly it's coming very easily. There's just a little bit of work at the end. Okay, but a consequence of this is that n is parallel along this hypersurface is equivalent. So if that's true, then this is equivalent to the hypersurface being totally umbilic. Okay, because if it's totally umbilic, the trace-free second fundamental form vanishes and both things vanish. On the other hand, if this thing's parallel, then this thing has to vanish, so the trace-free second fundamental form has to vanish. So, so there's a very nice interpretation for the normal tractor being parallel along the hypersurface. Okay, so the next sort of fundamental thing when you're doing pseudo-Riemannian geometry, the geometry of hypersurfaces in pseudo-Riemannian geometry is the Gauss formula. So the Gauss formula relates the ambient Levi-Civita connection to the induced Levi-Civita connection. So remember, if you have a submanifold and a pseudo-Riemannian manifold, and if the normal or conormal is not null, then you get an induced metric on your submanifold, so it has its own pseudo-Riemannian geometry, and you can compare, or try to compare, the induced Levi-Civita connection of that pseudo-Riemannian structure of the submanifold to the ambient one, and the link is the Gauss formula. So, so let's just recall that. So if you have a vector which is in a section of the a vector field for the submanifold, I want to think of that in the spirit of the way I'm doing things here as just being a section of the ambient tangent manifold such that NA VA equals 0. Okay, so that's how I want to think of the vectors in the submanifold. Okay, so that being so, I can use the ambient Levi-Civita connection to differentiate this vector. And then I could project that. So let's put a little underline here to mean we're only going to do it in tangential directions. But then I can project this with this pi CB thing, right? So this is just this Kronecker delta minus NN. So this just projects this back. So after you differentiate this, this may not any longer be tangential to the submanifold, so you project it back. And this defines a connection. And in fact, this gives you the Levi-Civita connection. Because it's easy to show that when you do this, you get something that preserves the induced metric on the submanifold, and you get something that's torsion-free. So this gives you the induced metric. So, so what this is it's delta BC minus NC MB grad A VC, which is this tangential direction using the ambient connection. Hit it with the Kronecker delta. And then I have this term here. Okay, but here I can move, because NC kills V, I can swap these around with a change of sign. So this is grad A VB plus, I can bring the V out, NB grad A NC, right? Because I've used that this holds. And therefore, and this is projecting back into, so this is a tangential index, and this projects this because this is tangential back in, so that's really the second fundamental form. Okay, and so that's the Gauss formula, basically. Okay, so that's a very basic tool when you do Riemannian submanifolds. So we want the analog for conformal geometry. Wouldn't that be useful? Now we've initially got a immediate problem, because here we use the fact that we can very simply interpret the tangent bundle to the submanifold with just a subbundle of the ambient tangent bundle. When we have a conformal submanifold, we have, so here's our conformal manifold, and we have this conformal, we have this submanifold here. Now it's true that this conformal structure, each metric in the conformal class is going to induce a metric on sigma, and as you range over the different ones in the conformal structure, you'll get an induced conformal structure on sigma. So this induced conformal structure on sigma will have its own tractor calculus that it knows and loves, and the ambient structure has its own tractor calculus that it knows and loves. But are the tractor bundles even compatible, right? So here we had the tangent bundle, so life was easy. So first of all, we have to see, are the tractor bundles compatible? So, so before we had T sigma going into here, we want the analog for the tractor bundles. Okay? Well, certainly we have this normal tractor, so we can form the perp to that inside the ambient tractor bundle along sigma. Okay, so this is the ambient tractor bundle, but along the submanifold. And sitting inside there, we can look at the things that are orthogonal according to the tractor metric to the normal tractor, just by analogy with pseudo-Riemannian geometry. Okay, now this obviously has rank 1 less than the ambient tractor bundle, so it has the right rank to be the tractor bundle for the submanifold, but is it that? Right? So, so we want to compare it with the tractor bundle for the submanifold. Okay, so as I say, it's got the right rank. Well, actually they do compare. So let me just put a theorem here. There exists a canonical map from n per, whoops. So it's an isomorphism to this intrinsic tractor bundle. I'll call it the intrinsic tractor bundle. And it preserves the metric. what I mean is that the restriction of the ambient tractor metric to this agrees under this map with the tractor metric here, and blah, blah, blah. Yeah. Okay, so the proof is just a formula. So, well, yeah, there are other ways of saying it, but let me just give you a formula. Okay, I'll put it up here. So here's nperp. Take this in here. So think of this sort of in the scale G, and take something in there. So sigma mu rho, as usual, a standard tractor in there, except it's orthogonal to n, and map it, call this star, to sigma mu b, I called it b here, let's do that just for fun, minus h mb sigma rho plus 1/2 h squared sigma. It's perhaps a bit confusing having sigma in the top. This is no relation to the scale or anything at the moment. This is just a general tractor. There happens to be an nperp, and I'm mapping it here. That's the mean curvature squared, and so on. So there's a formula like this. So this lives in the intrinsic tractor bundle in the scale G bar. So G bar is supposed to be the induced metric that's induced by G on the submanifold. So it's the compatible metric, and you calculate all this in that compatible metric. And the proof is that this just, so using that NA mu A equals H rho, and that H hat equals H plus NA epsilon A, you can deduce that the right-hand side transforms according to triple star. I mean, it transforms like a tractor for the induced. It's a thing I called triple star the other day. So for the induced transformations over here. Okay, so this is just the transformation of the mean curvature. What's this? Well, this is because this thing's orthogonal to the normal tractor. We have to have this relation. Okay. And then it's easy to see that the tractor metrics agree. So I'll just leave it as an exercise. Actually, what makes the exercise easy is that you can find a scale that makes the mean curvature vanish along the submanifold, at least locally. What's that? Oh, where have I got that? Yeah, probably, let's see. Yeah. Thank you. Wrote it wrong in my notes. Yep. Okay. Okay. So from now on, we'll just identify. We'll just think of this as being that. Okay. So we'll just identify them. I won't bring it up all the time. Okay, but that means that we can, what I was just saying then, but I had that typo, is that you can find a scale locally that makes the mean curvature vanish. So then this, then those tricky terms go away. That's why it's easy to see that the metrics agree, for instance. Okay, so now we can just identify this nperp with the intrinsic tractor bundle, and that makes it easy now to compare the tractor connection of the intrinsic tractor connection with the induced ambient one. Induced one from the ambient one, the kind of conformal Gauss formula. So let's have a look at that. Yeah, perhaps I wanted to keep that. So I'll put this up. Okay, so on this intrinsic tractor bundle, which we're going to, I think of it as agreeing with NPERP, we have one, the intrinsic tractor connection. So this is just the tractor connection of the conformal structure of the submanifold. So this is the standard tractor connection of sigma with its conformal structure. And two, we have this kind of check version of a connection, which is defined by, when we apply it to some tractor. So this is really, it's a tractor in T bar, but we're going to think of it as an ambient tractor orthogonal to N. So this is in NPERP. And this is defined to be equal to, now the tractor projection, BC, of the ambient tractor connection in the tangential direction. So like that, if you like. Okay, so remember in the pseudo-Riemannian case, when we did the equivalent thing, we just got the Levi-Civita connection, right? So the analogous thing does not happen. So this is the kind of projected, restricted ambient tractor connection. And it's easy to see that this sort of thing always produces a connection. So it is a connection on this bundle. Okay, so we can compute the difference between this connection and that connection, and it'll be a one form taking values in endomorphisms of the bundle. So let me write it in a certain way. So grad A check VB equals grad A VB minus SABC. So this is this kind of contortion tractor VC. So here V, as before, VB NB equals 0. So it's a thing in NPERP. And we're comparing the two connections acting on there, and this is the thing that's measuring their difference. Now, by construction, these are both conformally invariant. So everything we're working with here is conformally invariant intrinsic tractor connection, and this projection, because this is just done by delta BC minus NB and C. The normal tractor is conformally invariant. The Kronecker delta is just the identity. So this is invariant, and everything's invariant. Okay, so this S is something invariant. So what is it? Well, I'm not going to compute it. So my students have computed this. So what's S? So SABC equals, well, first of all, it takes the form of one of these tractor insertion things, so BC. So this is just, remember in this XYZ calculus, this is XB Z bar BC minus XC Z bar BB. So when I gave you that XYZ calculus, I didn't put bars on everything. I'm putting bars on everything because this is the submanifold version of it. Okay, but this is a conformally invariant thing that puts one forms into endomorphisms of tractors, and and this S comes from doing that to a certain symmetric a certain section f of S2 T star sigma, probably with some weight, which I haven't computed just yet. Well, yeah, we can work it out. I forgot the weight. But, okay, so what is this f? So this is a thing called the Fialkov tensor. We call it the Fialkov tensor because it seems to have shown up first in the work of Fialkov. And one way of writing it, and I think this way might be due to Sean who's here. Is that right, Sean? Well, I better write it before you can judge. So A, C, B, D, N, C, N, D, plus the trace-free part of the second fundamental form squared AB minus then the length of the trace-free part of the second fundamental form squared over D minus 2 G bar AB. Okay, so this is the Weyl curvature of your ambient structure. You've got two normals hooked into that, so that's of course the conformally invariant thing because the Weyl curvature is conformally invariant. This is the composition of the trace-free part of the second fundamental form with itself once. So that's what this L0 squared means. And then this one, you're just finding the length of L0 and squaring it divided by D minus 2. So everything, each of the terms, in fact, are conformally invariant in this thing. Okay, so that's just a computation to get that. But now we have everything to get the Gauss formula because, well, on the one hand, this is kind of the version of the Gauss formula. So this proposition is one way of stating things. But if I'm to write it the way I wrote the pseudo Riemannian one, it'd be like this. So we have if you act in the tangential directions with the ambient tractor connection on one of these vectors which is orthogonal to the normal tractor, so you can think of it as being in the submanifold tractor bundle, if you like. Or perhaps I should do it like that. Then this is equal to the projection the tractor projection, and then I have to fix up the damage I just did. So that's plus or minus NB NC grad A VC. Yeah, by the way, when I was writing those projections with a minus, it should be minus plus, so when you have one of these projections, it's delta, and I said minus N, but it's minus plus depending on whether N squares to plus or minus 1. Okay, so so where was I? Oh, okay, so, and now we can play the same trick that we did over there. So first of all, this by definition is this check thing. And now we have plus or minus this bit here, but I can swap these around. So this becomes minus plus, and then I have NB VC grad A NC. And then we can use that formula up there, which remember gave us this L thing. So this is grad check A VC minus plus VC. Probably do want the NB there. NB VC LAC. So remember that the derivative of N, we called it this blackboard bold L. So this is the kind of shape tractor. So I think my student calls it the shape form tractor. And this one is grab A VC minus SA C B VD. So we get that plus minus plus MB BC LAC. And that's our Gauss formula. Whoops. So this is a conformal Gauss formula. Okay, so that's almost all I wanted to say about this stuff, except that these are the kind of first steps for developing a calculus for submanifolds. So suppose you wanted to construct conformal invariants of a submanifold, then you have a similar problem to constructing conformal invariants generally, that if you try and do it naively, it's very slow and painful. And in fact, if you look in the literature, the things that have been written about that are typically very naive, and there's hardly any invariants constructed at all. So usually just basic things that I've already mentioned today. But now you can proliferate invariants of submanifolds if we were going that way. You know, so you can form, for instance, this LAB, which is you take the submanifold version of the tractor D operator and apply it to the normal tractor, and so squaring that and so on makes invariants of the submanifold. So you can do LAB squared, or you can differentiate it some more with this. So you can square these things using the tractor metric and so on. So you can just play around now and construct. This is pretty bad yellow chalk. Construct invariants of submanifolds. So I've just had a PhD student finish whose job was to develop a lot of this stuff. So Yuri Vietkin, yeah, so there's lots of things that you can play with once you get this machinery going. But that's not particularly what we want to do today. So that's what I wanted to say about submanifolds, and we will use this stuff in the next lecture to say something about what happens on these conformal infinities under various assumptions. So we'll look at a sort of hierarchy of conditions. Let me just say a word about something else now while there's time, which is this Helmut-Friedrich's conformal system. So we're back to so this is sort of timely because this is a system of equations developed by Helmut Friedrich to study the Einstein equations in the setting of conformally compact manifolds. So he produces a system of equations that if you solve them, then you get a conformally compact Einstein manifold. So this is mainly for those people who perhaps already know about the Friedrich's conformal system, because it's pretty well known in relativity. So let's talk about it in the setting of Lorentzian signature. Well, asymptotically flat. The signature won't matter. So okay, so this means that the Ricci is assumed to be 0 near the conformal infinity. And the conformal infinity in that case is usually called scri. So there's the sort of forward null infinity and past null infinity, and together they're called scry. That's been mentioned in talks already. Okay, so from our point of view, we want to look at, so what we want to do is see that the system that Friedrich comes up with is really, in fact, almost the same as the tractor connections. So if we were working where Ricci was 0, then that would imply two things, that you have a parallel standard tractor. Okay, so that says Einstein, and that its length is 0. So that, remember, that says the scalar curvature is 0. Okay, so we should be looking at what equations turn up when you do that. Okay, well, remember how the tractor connection looks. So you have sigma mu rho. The tractor connection looked like this. So grad A sigma minus mu A, grad A mu B plus plus GAB rho plus PAB sigma, or rho AB sigma, grad A rho minus Scouten hooked into mu. Okay, so that was the tractor connection. So what this gives us is grad A sigma minus equals mu A. So these are just, from Friedrich's point of view, additional variables that are introduced. Grad A mu B equals minus sigma PAB minus rho GAB. grad A rho equals Scouten into mu B. So that's the connection. And then on the other hand, this thing here gives us that 2 sigma times rho plus mu A equals 0. And this part is the first part of Friedrich's conformal system. So the next thing is a integrability condition, or really a couple of integrability conditions kind of compactly put together. So I being parallel for the tractor connection means that it annihilates the tractor curvature. We've mentioned that before. So here's the tractor curvature, A, B, C, D. And so we have that equals 0. So remember how this thing looks is you have cotton here, vial here, 0 minus cotton, 0, and then we're going into this sigma mu rho. And so what you get out of this is this C-space equation, which should be sigma times cotton plus vial equals 0. So this is sometimes called the C-space equation. Or writing what the cotton is in terms of the Scouten tensor, we get grad B PAC minus grad A PBC. So this is C, probably BAC in my notation. So dividing by the sigma here, this is equal to sigma to the minus 1 times the vial tensor A, B, C, D. Whoops, vial hooked into mu equals 0. So the vial hits the mu and the sigma hits that. Okay, so that's an equation that one gets from this thing just being a parallel tractor sort of integrability condition. It has to annihilate the curvature. On the other hand, the contracted Bianchi identity says that this is a divergence of vial. G there, sorry. Now, according to our first equation, mu is grad of sigma. And so if we use that, we can actually compress this sort of, or combine these two results to conclude that grad A, reorganizing some indices, W, A, B, C, D equals 0. So you put this bit and that bit together, and you can and use the fact that the derivative of sigma is mu, and you get that this divergence of sigma to the minus 2 of the Weyl curvature is 0. I grad A K A B C D equals 0, where K A B C D, if you like, is defined to be sigma to the minus 1 W. Okay, and that and this is the last equation in Friedrich's conformal system. So it's capturing the conformal cotton condition, because on an Einstein manifold the cotton tensor vanishes, and if it's conformally cotton, that's what the C-space equation is saying. And this basically has information about the contracted Bianchi identity. And then in dimension 4, the contracted Bianchi identity is equivalent to the full Bianchi identity. So summing up what Friedrich's system is in tractor language, so it's first of all saying that you have a parallel tractor, which is this Einstein condition. It's saying that I squared is 0, which is the scalar curvature equals 0. And then it's this integrability condition that you get from having, if you have a parallel tractor, it has to kill the curvature. And then there's the Bianchi identity, which so any connection satisfies a differential Bianchi identity. So this is so the tractor connection satisfies a differential Bianchi identity, and that's really where the system comes from, if you like, Friedrich's system from this point of view. But then you think of those as you've introduced new variables and so on. So you look at it from a different perspective. Not as how they arose, rather, but they become the new equations. Okay, so that's where I thought I'd stop.